Hey, how are you, people? I'm so glad to be back. Uh, Come on, 10. So, hey, Abra Malik, how are you? Um, I'm guessing everything's fine with the stream. Like, you can hear me, you can see me. If no, please let me know here in the comment section. I think it will be a nice thing to start explaining why are we here. Everything's fine. Hey, Oib, thank you for joining us again. And I know I have something that I missed previous session, and I will reply to those questions. Actually, we're going to start that. But first, brief introduction. Welcome to this part two of neural networks using MATLAB. What we were seeing on the first session was a theoretical introduction to artificial neural networks. We saw the biological inspiration, how are they composed, like the each part of a neuron in a network, how many neurons are required, how they connect themselves. Remember, we have layers of n neurons, and we have number of layers that connects neurons outputs to other neurons inputs. Uh, what else? We saw a little of theory. Actually, it took us more time than I expected. and we didn't have the chance to enter to what a Hamming network application would look like. Uh, um, no good. Everything it's perfect. Okay, thank you. So yeah, in this session we are going to resume or learning in the theoretical part of how the ham network it's declared. Like again, I'm returning to this cooking metaphor because I think it's very accurate. The recipe of the network, right? Uh, if you miss something or you're not catching up with what we are doing, you can always stay on stream, try to learn whatever you want, whatever you can, sorry. And at the end, if you missed the part one, you can watch the recording of that session, and a lot of things will make sense. But yeah, let's start with the questions I missed for the previous. So let me, I have my notes here about that. Uh, I have the question of OIP. Theoretically, can we set matrix automatically? For example, as you said, if we want to add new quality, example color, we add it by hand. But can we add quality using the model? If the model thinks that apple and orange have other qualities, it makes add value to the matrix automatically. Okay, um, if I understanding right your question, you're talking about feature extraction. In this case, we are designing the network to just receive a certain number of parameters. Depending on the size of these inputs and the number of neurons, this will increase or this will adapt automatically. Yes. But for the network, it will not be related to either uh, shape, texture, or weight, or in this case, I mentioned color. It for the network, it just be numbers, and that's all. That's all the network cares about. For it to automatically detect other features, then we will be talking about deep neural networks. The difference actually between neural networks and deep neural networks, it's exactly that, the feature extraction. So in this case, we just set the algorithm to receive a matrix, or sorry, in this case, a vector of r size. Depending of r, it will declare and do the matrix, the weight matrix and the bias vector and all that stuff. But it will need to be set again and to be trained again if you want to add another parameter, for example, of what I mentioned. Why is that? Because remember, the weight matrix here depends on the prototype vectors. So if we want to add another parameter, that meaning add another value to the input vector, then we will need to set the whole network again. So there's no like automatic way to do it here. It will be by design. It's and I will take the cooking approach again. It's like, for example, if you want to do a medium pizza or a big pizza or a family pizza. Remember, uh, for a medium, you will have to add, I don't know, 200 grams of flour. And for the big, you will have to add 300 grams. And for the family size, you will have to add 400. So depending on the recipe you're following and the expected output that you want, you will have to design and add other ingredients. In this case, other change the size of the weight matrix, right? I hope that makes sense. Um, so that is the answer for these questions, or if you ask us, let me know if that's clear. The next one is, and just okay, yeah, I think that's continuous here, and sets recurrent matrix automatically. Just curious how people made models like GPT, etc. Well, GPT, you can think in matter of complexity. These it's like doing basic maths, and GPT will be like doing differential equations and stuff. Like it's heavy and it's really complicated, and it's all very not that simple. Um, I love the metaphor of cooking, so I'll be repeating that. It's imagine this Hamming network like doing a hot dog. You can do a hot dog really nice. It can taste better, like really good. It can like be a good dish if you do it well. But I don't know if you heard of mole, for example, or that's a dish here in Mexico. Let me think of something more like international. I don't know, like the most complicated thing I think I can think of in cooking, it could be like ramen. I don't know if it makes sense, but the point is there are dishes that are very more complicated than others. And for example, in this Ahami network, you have just two layers. Like you have your sausage and your bread, and you combine them, and that's good. You have your hot dog. For GPT, these are called long language models. You have a lot of ingredients and a lot of layers in this case, and the way the layers are connected, it's not, for example, like in here that you have all it's called full connect network, because all the output are related to all the inputs in each layer. In the LLMs, this can be very different. The functions and stuff, it can be really interesting. Also, I encourage you to take a look to how these LLMs like GPT works internally, and how the architecture of that is. If I have time, I could take a look to one at the part four, like when we are done with the planning. But yeah, great question. Uh, okay, I have another one from XPD Kaysun. I think you're not around because I don't see your name. But yeah, your question was, can we use Octave or Python instead of MATLAB for this? Yeah, for sure. I mean, I am only doing this on MATLAB because well, MATLAB it's a really cool thing, a really nice tool. I also am trying to do more like research stuff, and in my school they provide us with the license, so it was a great option for me. But also I shared at the previous session some resources for Python. Actually, I take a look at the code in Python that Jacob Casati made, and I translated to MATLAB. So it will be better for you if you do it on Python. I'll be doing MATLAB just because it makes sense for me, right? So no worries about that. Do we need MATLAB for the next session? I recommend you to have it because it will be simpler to follow the program. But if you don't, again, there's always Python, the great Python, because I don't have MATLAB. Okay, don't worry. Thank you. Thank you. Okay, and that's all the questions I have pending. So I see another one, and green one, Rich Master One. What about large reasoning models? Do they have more layers than LLMs, or what makes them different? I don't know if they have more or different, but we can look for them. Like it's the same. For example, just to answer this in general, there are family of networks. Actually, there's a great resource I am thinking of now. Let me look for it because you will love it. It's called the neural network zoo or something like that, and it's a graphic showing like different types of architectures, and then inside these types of architectures you can find specific models, like for example the perceptron, or the Hamming network, or R-line, or this is the ones we are covering in these sessions. Is a math a necessary thing for working in MATLAB? I don't know. I think I didn't understand your question, Avram Malik. Sorry. Sorry, I said Avram. Sorry. I have now Malik. It's math a necessary thing for working in MATLAB. You're meaning like knowing how to do math or stuff? Yeah, yeah. You can think of MATLAB as another language, just like Python and stuff. It's kind of different, but it helps you because it is, as the name says, it's matrix laboratory, and it was built specifically for working with this type of data for matrices. So in Python, you have to do NumPy because um, it's better. In this case, imagine like MATLAB, it's working with Python and NumPy. So it's just like that. JavaScript, JavaScript is more similar like to Python. In JavaScript, you can also do matrices and stuff, but again, you will be better doing complex stuff with other libraries that can help you manage numbers. Because at some point, again, JavaScript was not made for data science, so you can do it. And again, JavaScript is beautiful because you can do whatever you want in JavaScript. But again, there are some tools that are better for these scenarios. And in this case, MATLAB, I think it's a great tool because it's it has native support to matrix operations. That's the only reason I'm using MATLAB. Um, Plus, it has a suite. Well, they call it apps or something like that. That helps you design neural networks like just with blocks, and it's great. And it's like I will teach you how to do that at the part four. But yeah. Now let me look for these resource I was talking about, the neural network zoo. You will love it again. It's great. Give me a second. I will look for it very quick. Here it is. Oh, I think I don't have the. Yeah, I think I don't have the link. But I will send you the PDF directly on Discord. Yeah, I will send you the PDF directly on Discord. That will be a better thing. Here it is. So let me start sharing my screen. Screen one, allowed, and here we are. Here we are. Um, I liked how I was looking myself in, yeah, in circle. Looks Looks more beautiful. Uh, 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 oh no. Well, this one. Nice. Great. Let me see because I saw some other comments. And can we build commerce level AI projects using MATLAB? That's an interesting thing. Um, yeah, I will say yes. Yeah, definitely you can. It's a common thing. No. Um, like privately on Discord? No, I will share it on the general chat. Give me a second and I'll do that. And can we build commerce level on AI projects using MATLAB? Well, again, you can. The thing here is that one of the things you will realize here is that the hard thing is to trying to find the accurate values of the network once it's well designed, like the weight values in the weight matrix, the bias and stuff. And that's called the learning process for AI. And in that, once you have them, they will not change. So unless you want to add more features or some other necessities to the network, right? So you can do that processing in MATLAB, and then take the answer, the weight and the bias and all that come inside the proper network once it's trained, and apply it to another network in any other language like Python and etc. The thing you want, it's the values of the weights and the bias of the network well trained. Um, so yeah, I'm opening Discord, and here on Global Hack Week there is the Data Week. I'm uploading the file. You should see it now. Yeah, already shared. Nice. Okay, so that's this one you're seeing here, and it's a great question from Grish Master. Uh, Here, for example, this is the graph I was talking. Uh, sorry, yeah, this is the graph I was talking of. For example, we have these deep feed forward. We have graded recurring unit. We have these pairs AI, the convolutional networks, deep convolutional inverted graphic networks, liquid state machines, the GANs, generative adversarial networks. Um, in this one, they didn't include, for example, the LLMs or the ones the one you asked, like the LRM, large reasoning model. But the family itself, it's just like another layer of abstraction of how the architecture is built. The specific case for this, for example, in this case, we have perceptron, which we will cover, feed forward, and deep feed forward recurring neural network. We will doing an RNN, the Hamming, you know, but it's just an specific case of this RNN because we have the feed forward layer and the recurrent layer. And the output, we don't need a specific layer for that. We just interpretate the data from the recurrent neural network. We could add another layer, but then it won't be specifically Hamming. It now can be another thing. Um, but yeah, hope this answers your questions. And it was a great question because you make me share this great resource. Thank you. So now returning, I think there are no more questions here. You're right. Thanks. I'll try to remove this comment. Well, I will need to be logged in Twitch, so I don't think I'll be able to do that. But if any one of you are moderators, feel free to remove that comment. But yeah, thanks. Let's return here. Let me drink some water. Nice. So, um, yeah, no worries. Uh, Sorry, I was reacting to this comment. Thanks for the explanation. No worries. Turning to this Hamming network that we were taking a look, we saw that feed-forward layer. It's composed by the Perlin function, and the weight matrix. It's said to be the transpose prototype vectors of the inputs we want to predict. Sorry, to classify. That's an important distinguish there. Um, where did you post the PDF? I don't see it on general. No, I posted on the Global Hack Week section, Data Week channel. Yeah, thanks. Oh, exactly. Okay. Um, that's how it's defined weight matrix in the feed forward layer. Remember, if we want to classify more classes, then we have to add more transposed prototype vectors here. It doesn't matter the size, they just have to be squared. What does that mean? I cannot add a prototype vector with two values, another one with three values, and another one with four values. They all four should be they all uh, n number of vectors you want or number of classes should be the specific the same size. Sorry, the same. What happens, for example, if you don't have information for, I don't know, for a reason you don't have information for the banana weight? Imagine in our previous example. Well, just add a zero or a value number. In this case, a -1 that represents the negative, right? But that should that respond with accurate classification? Well, the question is no. But for designing purposes, it should be square. I have another question. Alberto, what are the advantages to use MATLAB instead of normal Python? Again, MATLAB supports these metric operations that it's very important here for the purposes in a native way, and that's the main reason. Like just like that. Uh, so if you want to do it in Python, it's okay. It's totally fine. Um, Returning, that's how the weight matrix for the feed forward layer is it's built. The bias vector, again, it's built on the number of uh, prototype patterns we want to classify. In this case, we have two, so we will have two elements of the value of R. And R in this case, it's three, since these three vectors, since these two prototype vectors have three elements, right? If remember the example, we wanted to add another one. In this case, this column represents um, shape. This one represents texture, and this one represents weights. If we want to add color, that's okay, that's fine. Then R is going to be 4, and this will be 4, 4. If we want to add another prototype version, meaning, for example, a banana, if we want to classify this is orange, this is apple, and we want to classify a banana, and keeping the four element we have here, then bias will be uh, different. I know seeing a PDF it's not that helpful, so that's why I included this part here. Now I okay, you should see this. Let me know if you don't. You should see a screen. I'm trying to writing on this, so you can understand me better. And I'll make this bigger. This will be the feed. Oh, sorry. Feed forward. I don't know why these lines appear. Maybe it's full capacity. Uh, Let me try to delete them. Feed forward layer. In this case, remember we have two prototype vectors, P1 and P2. This is orange. Wow. Uh, Pencil have own. I think it's the screen sharing the thing that it's moving the pencil, but I will try to do my best. Sorry. Orange, apple. And let me remember the values for this. One, well, yeah, they were here. 1 minus 1. This is P1. This is P2. This is 1 minus 1 minus 1. This is 1 1 minus 1. Isn't it? Yeah, exactly. So now, in the feed-forward design of this network, W of 1, meaning the W, the weight vector of the feed-forward layer, the first layer, it is the P transposed of the prototype version vectors. This is this one. This is the same we have on the book, right? Till this point, no problem. The bias we mentioned, it's a column vector of error values of number of prototypes. So this will be 3 and 3, right? Now, now the example. I will add another value here of 1, minus 1, and minus 1 representing the, I don't know, the color, right? So for this, the color will increase the value of R. And in this case, this no longer works. This should be this one, 4 and 4. Now, if I added another class that I want to classify, saying, for example, banana, saying P3, and this will be 1, 1, minus 1, and minus 1, for, because we now have color, and also I need to add this here and this here. Well, let's delete that. Oh, sorry. And this will be now this 1 minus 1 minus 1 minus 1. This will be 1 1 minus 1 minus 1. Okay, how the weight matrix is going to change? Remember, we will have then to add the P1T, P2T, and P3T. and this will be like this: 1 minus 1 minus 1 minus 1, 1 1 minus 1 minus 1, and this last one, oh, this is really similar, so we'll add a minus 1 to here. 1 minus 1 minus 1 minus 1. Okay, and minus here because our way this will be same. um, yeah, and the bias same, we will have to add another r, and this will be 4 4 and 4. So this is how we can change the design of the feed-forward layer for a Hamming network. Everything it's clear here. No problem. You and just ignore the lines. We can understand. Okay, nice. Thank you. So moving on to the next part. Well, before we move on, remember the output value of this is and I will add it with this rep. A is going to be W1 times P plus the bias, right? Okay, and this is the value of A1. Remember, this actually has a secret part that is the purely that it's here, purely. Oh, I add an extra E. But this, it's exactly the same as not showing purely. So that's why we are not showing it, because it's the same, you know. But it is important to have that in mind. We cannot create a a neuron without the transfer function. Nice. So, meaning that if we replace the values, this will be this one, right? So, no worries. The recurrent layer, and let's add another here. Let's create the recurrent layer. I think the lines just popping up, it's stopped, so we can continue. A2, the first part, it's going to be A of 1. That's set W1 P plus B1, right? I think I forgot the one here. Okay, no worries. And here, because remember, biases are different. And this is called the initial. Oh, I think I'm. Yeah, so sorry. I wasn't showing the full screen. This is called the initial condition. Then a 2t times 1, it's going to be the puzzling. Oh, there it is. We celebrate before time. Puzzling of W2 times A2T, just like that. Being W2 defined as a matrix with one diagonal values minus epsilon in the corners. What's the value of epsilon? Epsilon is said to be not exactly, but approximately a value between 1 s minus 1 and 1. So in this case, s being the number of neurons we want to change, it's 2. So 1 divided of 2 minus 1, um, this is just 1. No, let me check something. I think it was not from that to 1. Uh, uh, yeah, it's less than this. Sorry, not minus 1. Being less than 1. So in this case, epsilon, we can say it's around 0.8, right? And we will see how these epsilons affect. Uh, Actually, sorry, we can't see the screen. Oh my god. Oh, yeah, I think you were talking about a second ago. So sorry about that. Yeah, my bad. I'm going to return here just to be sure that you take a look of this. Uh, and now we're in the recurrent layer, right? And we are creating the weight matrix for the recurrent layer, that meaning the second layer. Here, uh, we propose a value of 0 of epsilon being 0.5, half of the minimum value, that's fine, of the maximum value, sorry. um, and here, remember, we don't have a bias because that's the design of the network. There's no more reason than that. The output doesn't require a bias, so we add 0 as bias. Here we have an example. For example, if we add another p that's different, if you take a look, this it's not same as the ones we had before. In this case, put attention to the black p's, p1 and p2. That we are not adding banana yet. We are going to take a look to that in a second. But 1 minus 1 minus 1, 1 1 minus 1, this example P that's not part of the prototypes, this is the one we want to classify. And again, if we as humans will do it using a Hamming distance, which one you will think it will be more closer to? Like what the classification will draw us. It's supposed to me to be more similar to the orange, sorry, than to the apple, because in the this value we have just one, the first different, and for the orange, sorry, and for the apple we have two difference, the first two. But let's do how it's done that in numbers. The output of the feed-forward layer, that meaning the first layer, remember this one we set here, will be this. We have the weight matrix 1 minus 1 minus 1 1 1 minus 1 multiplied by this vector, this input vector, plus the bias that said the output of a 1 will be for 2. Nice. And then for the feed forward layer, here, for example, they are proposing the same, an epsilon of 0.5, meaning the weight matrix will be like this: the one value diagonal and the minus epsilon in the corners, multiplied by the first element, here, A in the first time will be puzzling of the initial values times the weight matrix. So weight matrix of the second layer, times the initial values, which is the output of the first layer, and that output will tell us 3 0. The puzzling of that, it's saying 3 0. Remember, puzzling, the only thing that it applies, it's if the value is negative, it sets it to 0 directly. Um, so this is A2 one value. We need to do it again, right? For the next iteration, we'll see that A2, it's puzzling weight matrices of the second layer times the previous value. In this case, A1, which is this value here, and not anymore the output of the first layer. So that's puzzling. The weight matrix doesn't change. The weight matrix it's already designed for this second of this of for this second layer. The only thing it changes it's the p. In this case, p it's A1, and we have same puzzling of 3 and minus 1.5. This is where the puzzling function, a transfer function, comes and sets to be minus 1.5 to be 0. So we have two values that are equal, meaning that we're done. This means, and I will have a moment here to explain uh, what the output, how we can interpret the output. But this having two similar, like the the output of the A1 and the A2 equal, means that the recurrent layer it has to stop. Again, it's like in a for loop. You have to say how many times, or in a while loop, until which moment we have to stop. Remember, we have to have different stopping values. Give me a second, and I have them here. Uh, 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 yeah, stopping conditions for the Hamming network are two. Having just one element of the vector that's different from 0, meaning uh, just one of the elements of the vector it's different from 0. Like in this case, we have 3 and 0. One, this 3 it's different from 0. So the first condition is met. Here we call stop. But we need the second condition, which is the result of the immediate next iteration needs to be equal to the previous one. So that's why we do it again. We make the second iteration. We see that result it's meeting the first criteria again, just one element of the vector being different from 0. And this one it's exactly the same as the previous one. So this is where we stop. These are the two conditions or the two criteria for stopping here. Like in mathematical, in programming, you need to add a third one because if you don't design this well enough, you can be doing a recurring cycle many times, and like these jokes about the infinite loops. So we need to add there like a counter to say just try to do it 100 times, 1,000 times, etc. But yeah, that's just for the programming application. For mathematical, these two criteria are enough. Nice. So let's add. We see how this works for an example vector. Let's add the banana classifier and let's try to test it with another vector. Do you like it? Let's do it. Let me return here. Yeah, let me return the screen here and let's make the changes with orange for the banana. So we already made our changes here for the banana on the feed forward. We have our weight matrix and our bias. Let's change the recurrent layer in for the banana, right? So this won't be applying anymore. And what we have should have, sorry, this will be a matrix like this with minus epsilons in the corners and ones in the diagonal because now we have three classes. And Alberto, what about four? Well, these will be exactly the same. One, two, three, four. Fill the rest with minus epsilon and so on and so on and so on. But for the moment, this one helps. And if we take the values of this of course it's minus 0.5, minus 0.5, minus 0.5, minus 0.5, minus 0.5, and minus, well, let me make more room for the values. Minus 0.5 and 1. Nice. And that's all the change we need to do. Now, we could perform like the, how to say it, manual task of doing matrix operations here, but we are programmers and we are lazy. So let's open MATLAB and take this to MATLAB. Would you like? I'm opening a new MATLAB file. This is XL. Sorry, no. What's the name for this? They have a different name. It's not a .m. I mean, if you're familiar with MATLAB, there are live scripts and scripts. The scripts are .m and live scripts are .mlx. Yeah. I'm opening a new one. Give me a second. Yeah, I have it here now. So let's start coding. Um, Remember, first, I'm going to close this one, the neural network zoo, and let's see. Let's code first the W1. W1 was, and let's define first, sorry, our vectors. First, orange, this will be P1, and this will be 1, minus 1, minus 1, and minus 1 we mentioned. Or P2, it's apple, and this will be, uh, I can see that JS wallpaper it's going up. Yeah, I love JavaScript. I cannot resist to it, uh, and I won't hide it or anything. So yeah, P2 will be 1, 1, minus 1, and minus 1, right? And the last one, banana, banana. Oh my god, I'm writing terrible. Yeah, banana. This will be P3, and this will be 1. No, the shapes we call this. In paper, I write this minus 1, minus 1, but I think this will make sense more 1 because this is texture. Minus 1 in weight, and color. Let's talk. Let's imagine banana and apple have a positive value, right? So we have our prototypes declared here, or weight matrix for the first one. Another thing I have to mention is I am doing this wrong because I am doing this like if they were like row vectors. We actually need them as column. So let me change just this. We can run this live script just to test the output since I'm not adding a semicolon here. If you add a semicolon, the output won't be shown. If you don't add it, the output will be shown. That's the only reason of semicolons here in MATLAB. Let's run this section. And you will see now we have the vectors as columns. Nice. And here that was important because here we have to declare P1 but transpose. How we transpose here in MATLAB, we add this quote. Um, another, the other row will be P2 transpose, and the third one will be P3 transpose, right? So now we've done this again, and we have our weight matrix as we wanted, right? Remember, we want that like this. Exactly. Some values changed because I changed, for example, the last of the apple and like all the banana one. Here, I just wanted to prove how it was done. Here, actually, I'm thinking more of the real data because remember, the first it's about shape, the second about texture, the third about weight, and we are proposing different than the example of the book. A color one, right? So it can make sense more. B should be, well, B1 should be same, or in this case 444. 444. And we have it like this here. Nice. And A1 should be W1 times the vector P, not P3, P1 we are trying to, a vector that we want to test, plus bias 1. Yeah, of course. In this case, test P, let's call it, we will do one thing like this, but same. And before even performing anything, let's think which one we think will be the accurate classification. Different, yeah. So this one's different. We can add one different, one different, no different, no different, two different, one different, no different, no different, no different, no different, one different, and one different. So it's closer to be an orange, right? So this should be orange. Nice. And we are going to change this to test P. Nice, nice, nice. So what's the output of A1? A1 give us 6, 2, and 4. Nice. Now we are going to create weight 2. And for creating weight 2, we are going to need an epsilon. Remember, we proposed by design an epsilon of 0.5. Weight 2, it's going to be a matrix of ones. Well, we can do this for performing filling the space, but we can do it manually also. That will be 1 minus epsilon minus epsilon. Next column will be minus epsilon. Sorry, my next row, minus epsilon. 1 minus epsilon. Next one will be minus epsilon minus epsilon, and ending in 1. So let's run this to check that our way to it's as we wanted. Perfect, nice. Now our A2, it's going to be the function puzzling, sorry, of W2 times the previous value, which is A2 0, in this case meaning A1 plus nothing, and just like that. But we haven't declared the puzzling, so let's do that. I'm breaking down this in another section of code. We are going to create a function called that returns the y, and this is going to be puzzling. It receives an a, and for and well, it makes more sense, and we're going to end this function. Everything meaning n. I want to take a look to the, well, you will like to take a look, sorry, to the functions, how we were declared. We have this now, puzzling. If n is bigger than 0, and it's the same. If n is less than 0, then a it's 0. So in this case, we will be returning a. It doesn't matter how we call it. If m it's less or equal to 0, a it's 0, and else a it's equal to n. And like that, we have our function. We run it, we don't have a problem. We pass it, we don't have a problem. So let's see how these, let's call a1 slash 1. And for these reasons, let's call this a2 slash 0. And remember, this a2 slash 0, it's exactly the same as a1. Nice? Nice. So let's run this, and we will see the output. A2, it's the same as A2 slash 0 in the first time. This will be exactly the same as A1. A2 for the first time or for the second time, depends where you start counting, it will have different values. But I'm seeing that this is not working as it used. It should, sorry, because puzzling should return only positive values here. So we are receiving 3, -3, and 0. So this is not working as it should. Value assigned might be unused. If n, okay, the problem thing it's that we are receiving a vector, and here we are just comparing anything to a scalar. So what we can do is do this different. I have this, just let me open me transfer function. I already declared this purely puzzling, yeah. There's another way to do this. With a function that's already built in here on MATLAB that's called the max, which returns the positive linear function, right? So let's run this again. And see how it changed. So we have 3, 0, and 0. Um, then you can be think, hey Alberto, yeah, you told me the criteria for stopping, but you didn't tell me what the output means. Actually, we haven't met the criteria yet for stopping because we now have the only one value, not zero value in the vector, but the second criteria was have an immediate value exactly the same, and this is one, this is two. They are not exactly the same, so we need to do it again, right? So a2/2, this will be puzzling of w2 times a2 1, the previous value, the immediate previous value, and now we run this again. And nice, a2/1, a2/2. These two have the exact value. So the immediate previous value, it's the same, and the criteria of having just one not zero value is met. So now we can stop. And that's it. How we interpret this for Hamming networks, specifically for this Hamming network. For Hamming network, we interpret the position of the non-zero value as the classification. So remember that we define our first uh, layer weight matrix as the transpose vector of the prototypes. So P1 will be the first position here, meaning that the non-zero value here, in this case is 3, but non-zero means that it can be 2, it can be 1, it can be 100, it can be whatever, just a non-zero value. That's why the criteria for stopping is having just one of these. Um, the non-zero value of this, it's the first position, meaning the first position and orange. And this, accordingly, what we created, it's that it should be an orange. So everything's fine here. Nice. Let's test it with another p vector, right? And I'm going to design it on purpose, test 2p, to be minus 1, 1, minus, no, sorry, 1, yeah, and 1. So the different, it's 1, 2 different, 3 different, 4 different. It's all opposite of orange. This won't be an orange. Different, 1, same, 2 different, same, 1. But this should be classified as a banana, right? So let's do this all again. We don't need to redefine W, and we don't need to redefine epsilon. Just let's do the A's again. Right? So let's run this section of code. And this test 2. The first output tell us this is the first element, like the vector we are going to pass to the recurring layer. Actually, this doesn't tell us a lot, but once we enter the first, we saw, oh, okay, I'm probably doing something wrong. Uh, uh, yeah, because I'm passing the same test. Actually, I was like, what? It was classified as an orange, but yeah, I'm passing the same test vector. This should be test vector 2, test 2p. Okay, nice. Sorry, uh, it happens. So cool. A1 is this vector. A2 is this vector. See how this time now it does not tell us the at first time. Um, a non-zero value. There are two non-zero values. So we need to do it again. And we do it again, and this time there are also not two zero values. So we need to do it again. So in this time there are, yeah, one only one non-zero values, but since, well, the other criteria was to do this until we have the same output twice, we need to do this one more time. And this will be A2 the third time, and this will be multiplied by the previous one. So we run this again, and we have now the two values again. And this is the missing criteria for stopping, not in the previous one. Here we could inspect and see that now the prediction of being a banana can be right, but the criteria tell us to stop until it's confirmed in a second time. Here we are for sure. The output tell us the non-zero value, it's in the third position. Third position corresponds to the banana classification, right? So that's how we design our network, the Hamming network. We take the one that was in the book, we add another classification, which is the banana, and we even add another criteria, which is the color, right? Um, nice. I think there's no question till this point. We are going to do a little bit more exercise, and I will show you how I created this to be a little bit more complex, because in this time we have to do a lot of manual stuff. Actually, you can do this and keep making iterations like I did, and just see the outputs and analyze it. And for learning reasons, that can be good. But as Malik asked, should this be in a real world application? It looks like learning code, you know. I will show you real world application, and I will show you how you can build it. Just let's make a quick pause for us to understand this, for us to be calm, and we will be back in less than 5 minutes, right? If you have any questions, drop it on chat and I'll answer it. So be back. Don't worry. Hey, I'm back. Um, I see no questions were asked on the comments, and that kind of, I don't know, that worries me because even if you're understanding anything and everything, sorry, um, you will be asking a lot of things. Like a good class is where you finish with a lot of questions. So I will try to do better. Um, and for that, I will show you the code of the transfer of the Hamming network in an object-oriented way, which I think it's a very good approach talking about these networks because for me it helps you a lot to understand like each part, right? Let me show you. So I have this Hamming network. It is the implementation of the Hamming network. We define the class Hamming network, and we have the properties. The properties of the Hamming network are the feed-forward layer and the recurrent layer. So in the constructor, we set the properties to be the feed-forward layer and the recurrent layer. Um, we pass the prototype to the feed-forward layer as we were doing until this point, and then we create the recurrent layer, and for the recurrent layer we don't need to pass anything. Um, so once the class is defined and we create an instance of this object, we set a function, a method, because it's a class, yeah, to classify. So we set a1 being the output of the feed-forward layer using the propagate and the input object. The recurrent result is the object of the recurrent layer in one and the AAS, right? The result of the whole thing, it will be the compat function, and we will talk about that. This compat function, it's only a transfer function to tell us which one of the uh, vector values, it's not a non-zero, of the recurrent result. And then we display the Hamming network result, right? So very clean, I think. I'm not talking about my code, actually. Again, I translate the Python code of Jason Casati to this MATLAB thing. Um, but I think it's a really, really clean solution to take a look to these at object-oriented programming. So we have the Hamming network with the feed forward and the recurrent, like that. Just declare them on the constructor, and to classify, we pass the inputs to the feed forward, then we set that on our A1, and we feed the recurrent with the A1, and like that, we set the result of that to a compat function, and the compat functions tell us which class is the one we are looking for. Just like it. Nice. Uh, Malik says, "Okay, please tell me what is 1 plus 1." Um, I'm not sure, but I will say 2. If I'm wrong, let me know. Um, so let's open now how the feed-forward layer looks like here. Okay, for this we also define a class that's the feed-forward layer. The properties of this will be the weight, the bias, and transfer function. When we initialize this, we receive the weight as as a parameter, and since this comes by design, it will be like passing this value to the to the network, right? Um, Meaning, also we are feeding the network with the prototype vectors. So two birds with with one shot. As it's the size of the one of the first row. Well, since this is squared, uh, sorry, not necessarily squared, but since all vectors, all prototypes have the same length, we can take the one of the first of the second, because we're not sure if these have a third, right? But let's take the first, the one. Um, that's the only thing size do. So size takes a look to how long it's this first vector, and it returns the 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 first size, because remember here we're dealing with matrices. So matrices have two sides, the column and the rows. Even if it's a vector, remember a vector it's just only a matrix of one size in one of the directions. uh, so that's why we need to specify, give me just the first value, the length of the column. Then we set the bias to be ones times the times of the size, remember, times s. Set the bias as a pure size of the weights. Object transfer function, it's going to be purling, just like that. Where's declare purling? In the file I showed you before, where we have the purling, the puzzling, and the compet, right? And propagate, uh, well, this means that we are going to pass the output of this layer to the next layer. That's why we call it propagate. Uh, and we receive a result. TF in the feed forward layer transfer function will be this, W will be this, and bias will be this. We will be very transparent here with the output. And as you can see here, let's wait this for load. Come on. Okay. A1 will be exactly the same here. Result will be the transfer function, purely applied to the weights times the input, the P, plus the bias. And just like that. I mean, there's a lot of logging and displaying stuff, but the only thing, the only um, calculus performed here, it's this line. So very simple again. So let's continue to the recurrent layer. In the recurrent layer, we set weights and transfer function. We don't need a bias. The transfer function for this it's going to be puzzling, positive linear. The weights it's going to be an empty matrix at first, but then we are going to create that empty matrix based on the initial S on the size, and we are going to apply the diagonal of ones, and any other value it's going to be epsilon. So this is a more programmatically way to create the weight value of the second layer of the recurrent layer than this, like creating just one epsilon minus epsilon. Imagine taking this to the four, five, fifth, eight dimension, even more bigger than that. It can be really frustrating to code that. So performing this will be a better approach. And once we have the W for that, then we need to propagate to the recurrent layer, meaning passing values again until we hit the two conditions. First condition, only one it's non-zero, and the second condition, we have two values same. Here, I find something tricky. Actually, I thought of this before coding it, but A2 can be a little trick because this will change. This will be A2 anymore. The next iteration, this will be A3, A4. But changing the name of the values of the variables cannot be very good here. I could change this to be instead of A2, AT times, sorry, A T plus 1, but this is not a valid name. Um, we could be a T plus 1 and this A three plus 2 and stuff, but it's a decision I took when I was dealing with this. Just leave it like that. Uh, you created a better idea of that here with these indexes like the minus zero, slash one, underscore two, and stuff. Um, so keep with that idea. The thing here is it works. No? That's the important thing. So that said, we can. I have a fruit classifier example here that I created. So let's explore more examples, right? So this main script set the prototypes, the ones we said mentioned before, the orange and the apple. We have the prototypes in just one single vector. We have the test fruit that we are going to um, test. In this case, we are setting the epsilon to be 0.5. We pass the test fruit to the classified, but first we create the what's the word for this? The instance of the class here. So we create a Hamming network passing the prototypes, and we now have our Hamming function classifier. And again, the object-oriented programming approach, it's great because we have now a Hamming fruit classifier, but then following the same, we set the function Hamming network, we pass this, and we have a different Hamming fruit classifier. These exercises are on the book. You can take a look at them. This is exercise number one, where it's given to create a W1 with S7 and R equal 9, meaning 9 values, 7. Sorry, the size of this will be 7, and there are 9 vectors or 9 elements to classify. And that's the beauty of the object oriented, because all of this work done here, all of these lines, I mean, I know there are not too much lines, but it's resumed here in just these two. Create the instance and classify it. So you pass the vector you want to classify and an epsilon function, and you will receive this. They use purling, the weight matrix in the third forward layer this, the bias used is this, and we will see each output of the feed forward layer results. A1, A2, A3. Nice and nice. So the Hamming networks tell us this it's going to be an orange. And it's the very first example we created here until we change it. It's the same. So let's start taking a look to these exercises. For this one, that it's more complex and it's bigger, we create very different fruit prototypes. I call them fruit one, two, three because my imagination called tell me nine fruits. And here at this point, I didn't care about if this represented weights or uh, textures or colors or shapes or I don't know smells, flavors. It was a lot of elements to deal with. So again, in abstractions are just numbers, and they have values. So we create a test fruit. We use a bias of zero, an epsilon of zero, and we start predicting. And we have the W. Imagine doing all of this. Imagine coding this W of the recording layer, just typing it. It's a great thing that we have cycles, loops. Um, and the first output give us this. If when you understand the process, you will see that the prediction will be the eighth position. So let's go ahead and identify that. Yeah, it's the eighth position, right? So the fruit eighth is the classification. Nice. Compute exercise number two. It's using the previous W1 and repeat the experiment for these three different values of epsilon. The previous one I mentioned was zero, and it took us five recurrent iterations to get to the result. Let's see if we increase the epsilon to be 0.1. Well, well, it's starting to be a little bit longer. We need more cycles, but at the end, the prediction is the same. We see that the eighth position is the classification. So, in this case, and this is I want to show it with you, epsilon did affect, and the one we proposed and the one we are trying to do affects directly uh, the number of cycles it requires. So, what is the difference? And you can see it here. We start the first eight. The first iteration on the recurrent network with these values 1.75, 1.75, 6.25, and the next one it's almost half of it, 0 2 3 0 3 1. I mean, not half, a lot less than half. Like the change here was very big for this case, in which at this point the difference was very big. Like all of them were lower values, and the other one was 6. This big step change help us because we get to the value sooner. But imagine we have more parameters. Imagine we have not 9 classes, but we have 20, 30, 90, 50, a lot of classes, a very robust classifier. If some values here were more similar, alike, like a 6.20 and instead of a 6.25, these big steps, yeah, could make us reach an, an value sooner, but it also can lead to misclassify something because in these steps the resolution decreases, and this is what's happening here. Here we start with a lot of values different. We see more difference here than in the other one. In the previous one, we saw like 1, 2, 3, 4 equal, another 4 equal, and these 6 different. Here we see, no, sorry, it's this. Oh my God, it's this one. Yeah, One, two, three, the same four with more resolution. Here, one, two, three, four are equal, but the last four are also different. One, two equal, one different, and one different. So this gives us more resolution on the classification. And these steps on the changes, sorry, on each step, it's less. It reduces, like, not completely directly to decimals, but it reduced to full numbers, to from 8 to 7, from 4 to 2, from 6 to 4 to 4, 12 to 11, and that and so on, and we will continue until all numbers are zero except one. So in this case, you could think a better approach could be always to have an epsilon that helps you to get an answer sooner. But think of that. Think of the resolution that you're, as always, you're dealing with trade offs. So the quicker you get to the solution will not always be an accurate answer. In this case, it will, because the test case we're giving here, it's different. And for the Hamming network, it will depend also a lot in the in the prototype. Sorry, not the fruit related stuff, but the Hamming distance between these nine vectors. And if you have less categories, imagine not seven values here, but imagine three. Imagine you have only three values here, and you have uh, 19 or 18 prototypes. At some point, you will have the how to say this, the combination of numbers are require enough to be different, like some of them will be equal, so you will have two classes. And that's another condition you have to take in mind, for these, for yeah, for these networks specifically, because the Hamming distance between the prototype vectors should be different. You cannot put here two equal vectors, two prototypes that are equal, because in that case, one one thing that can happen is that the network doesn't converge to any value at any time. Then you will be looping to it. Or the other thing is that since you don't have only one non-zero value, then you will have an answer, or the answer could be wrong. So that's another thing to have in mind. 0.01, it gives us the Hamming result in 5, same as in 0. And if I add a negative epsilon, uh, we see that it's very interesting to have something like this. We reduce even the classification. Um, so that's the purpose of this exercise. Uh, so epsilon changes the level of difference. Higher epsilon means better accuracy. Lower epsilon means worse accuracy but faster. I wouldn't say it like that. I will say epsilon gives the resolution, and resolution in some cases it's very important. It doesn't mean always lower or better accuracy, but resolution is a thing. It depends again on the Hamming distance between your prototype vectors, and this is where the designing comes. The artistic thing we were mentioning on the first session, on the part one, about, yes, engineering have a rule, have a strict way to do stuff, but once the rules are set, and once this is scoped like in criterias, in number of elements, in boundaries. Once you have all of that, then you have to be creative and you have to do like the designing stuff. And designing, as I mentioned, it has the necessity to be a little artistic in every time. um, so yeah, for example, and I just don't know if this makes sense for any of you, but I'm web developer. So when I started, no one tell you well what the color of the box should be. Like, hey, create a web page. Yes, but what styles should I use? Well, there are rules, there are design principles, there are also engineering stuff that you need to take in count of, but there's also imagination and creativity that you need to put in your designs. Same here with the networks, with the neural networks, artificial neural networks. Um, you will have to do these modifications to your epsilons and try to test and see what it's better for your use case. Remember, if it performs well for your prototypes and for your test inputs, that's fine. And another thing here is that there could be multiple values that works for you. There's not only one value or one answer to your problems. They could be multiple things, multiple values, multiple weight values, multiple bias values, multiple epsilon values in this specific case of the Hamming network, um, that fits the necessity. You know, I agree. Thanks. Um, so yeah, that's a very important thing with the Hamming network and the epsilon thing. In this case, by design, epsilon and bias are not going to be changing. You know, that's an important thing. Sorry, I mentioned epsilon. So weights matrix for the feed-forward layer and bias are not going to change. They are strict, but for the recurrent network, remember changing epsilon means changing the weight matrix. We don't have bias, so epsilon it's a value that only appears here in the Hamming network, um, and it can appear in others. But again, don't that put that much attention on epsilon here. The important is that we need to adjust the weight matrix. Don't put attention to epsilon. The weight matrix is the one important because adjusting weights and biases in neural networks, it's the thing that it's going to give you the better results or the accurate results to start with in network designs. Um, so let's let's see all examples and then we can wrap up the session with some questions. I don't know if you have any question. And in the part three, we will see perceptron. We will see the perceptron as it is. I will introduce a new concept, which is the decision boundary, which also can apply here for the Hamming classifier, but I think it's more illustrative in the perceptron. I will see. We will see the decision boundary. And now in part three, we are not going to do only perceptron by design, but also we are going to do perceptron with training rules, meaning that we don't have to calculate weight and bias ourselves like the thing we're doing here, but we are going to make the perceptron learn how to classify. uh, yeah, thanks. Let's continue with this exercise. Create a W1 which with any S or R and epsilon. um, that to here, for example, the exercise tells us to create the values of W in order to don't make the output to reach an answer, and we will set it to hit only 100 times of trying that. Uh, Someone's calling me. Just give me a second. Sorry. Sorry about that. It was my mom. So I needed to answer. Um, yeah. So again, the exercise here is to design it to make it not giving us an answer. And there are many ways to do that. I mentioned it before. We can add prototypes that have the same Hamming distance, so they will. The criteria are not going to meet, and we will never receive a response. But also, we can make an epsilon to with a higher resolution. Let's put it that way. That 100 times won't be enough to get to the desired output to meet the criteria. So for what I think I created this with the second, like with the epsilon that doesn't give us response. But let's inspect the data. No, actually, I created that with the first with two prototypes with the same Hamming distance. So take a look at this. Um, for the first, we can see these two are equal, and the next time, and the next time, and the next time, and every time it will try to get a result. Since the Hamming distance between these two is the same, there will never be a criteria admitting that only one element is not zero value. So 100 times after that, and it says could not classify. Sorry. And if we inspect it, we as the designers will know, okay, the problem is that these two values are the same, so uh, probably, not probably, surely, the two Hamming distance for these prototypes is the same. Um, so yeah, compute exercise 4, create an W1 which any S and R that the vector of P shows. Okay, same. Here we need to misclassify based on epsilon. So the instruction says to create or design the network in order to, with the same prototype, with the same P, uh, test P or P vector, input vector, and different epsilon values have different classifications. So first, the test vector I'm going to use is this 1 minus 1 and minus 1. And with a value of epsilon of 0.3, the output is after 100. it says no output. Okay, I don't think I'm do something like this. Oh yeah, no, no, no. Yeah, for both it could not classify. Yeah, I remember this exercise now. The instructions I mentioned were correct, and I tried to do this a lot of time, but after analyzing it and thinking of this for a very long time, discussing it with some teachers, uh, I can tell you this cannot be done. um, since the two, yeah, the result it cannot be done just like that, uh, and I added these annex of the values I try and stuff, and that's it. Yeah, it was a tricky one. Exercise number 4. There are more if you want to check them out here on the book. There's a section dedicated for that. There are three more. These 3.7, 3.6, 3.5. No, I think no, yeah. I think these weren't from this section. Yeah, I think these were the ones. Two general network have two four inputs and six outputs. A single no. I can't remember where I take this exercise from. Well, don't worry. Uh, you can take a look to my exercises. These are on the link of the repo I shared before. But also in the book, you can find many other exercises to test your skills more with the Hamming network. And well, as I mentioned, for next part, we will reviewing perceptron. So I would like to know if there's any question to this point, if everything was clear. If no, I'm sorry, I did my best trying to explain. But also, I shared a lot of resources of how I created this knowledge, so you can create your own. Um, any comment or anything? Everything was very understandable. Thanks a lot. What's that? It reminds me of this domo. It was like a bird. Thanks. Okay. I hope you like this. I hope you understand a little bit better about the theoretical part we saw in part number 1 with this specific application that was a fruit classifier using Hamming network. Uh, we will review the perceptron. We can classify fruit again as an example. See you in 4. I think it will be in 6. My next session will be let me confirm. 1 second. Yeah, 11 p.m. ET time. Um, that will be 10 for me. Now it's oh no, you're right. No, yeah, I was right. 6 hours, 6 hours, 6 hours. So yeah, see you in around 6 hours. Bye, people. Thanks a lot for joining me.